Hello and welcome. This video is going to be looking at friction on an inclined plane and specifically the calculations that are involved when working these type of problems. I've done two previous videos on frictional forces and force normal. If you have not watched those videos, I highly recommend you going back and watching those because I'm going to use a lot of the terminology from those videos as well as concepts from it that you may not be familiar with, haven't already been introduced to it in your class, or if you haven't watched those other videos. So let's go on and jump directly into this and look at a diagram of an object on an inclined plane. Talk about that diagram, how you set it up, what a free body diagram would look like, and then solve a problem. Right? So here is an object sitting on an inclined plane. And what I always tell my students is draw out a depiction of the problem. So if it tells you that you've got an object on an inclined plane, draw out a rough sketch of an inclined plane and that object on it. Then you can start going about designating the forces that are acting. And the first force that you should always put onto any type of diagram is the force due to gravity or the weight of the object. So in this box, I'm going to put my point mass. And because acceleration due to gravity always points directly downwards, so does that force of gravity. And again, that'd be mass times gravity, or the weight of the object. The second force that's always going to be present if it's sitting on something is force normal. And recall from previous video that force normal is always acting perpendicular to the surface on which the object is sitting. So as a result, force normal acting perpendicular is going to be at this angle. That's my force normal. Now, if this inclined plane is frictionless, then I have to start thinking about the fact that there's going to be some type of motion down that inclined plane. And if there's motion down the inclined plane, then some type of force needs to be acting on it. But where does that force come from? Well, let's look back at force normal. If that force normal is the only force acting at that angle, then we'd expect to see that box levitating off the ramp, and we don't. What that means is there has to be some equal but opposite force acting into the ramp, and that is going to be the y component of the force of gravity. So we can draw in that component, and this is going to be force of gravity in the y. Some textbooks will denote it as force of normal in the y. Either one is acceptable. The other force that I now have, when we're looking at this, is that force directed down the plane, and that would be force of gravity in the x, which again, some textbooks will put that as force normal in the x, simply so you don't have three forces of gravity there. Instead, you can think about force normal acting in two directions, in the y and then in the x, and that's perfectly fine. The other thing that we want to notate on this particular diagram is, if you recall from geometry, when I've got angles set up like this, the angle of my ramp is going to equal the angle that I set up when I create this diagram. And that's going to help solve for math, because now looking at this, I've got a right angle, and going back to trigonometry, remember that sine always equals opposite over hypotenuse. Cosine always equals adjacent over hypotenuse. Well, our hypotenuse is that force of gravity, or mg. So what I can do is further explore into these equations and think about, okay, well, my side opposite is that force of gravity in the x. So therefore, force gravity in the x, or force normal in the x, over the hypotenuse. And when I'm looking at force of gravity or force normal in the y, that is my adjacent side. So I can set this up, force of gravity or force normal in the y over the hypotenuse. And that will let me rearrange and solve for the components of that force. So what I can do is go back in, say, okay, so my force of gravity in the x, or force normal in x, is going to end up equaling, cross multiply, the hypotenuse times sine of theta. Therefore, mass times gravity times sine of theta. And that will tell me what force is acting down the plane of that ramp. Likewise, I can look at my cosine functions. So, all right, force of gravity in the y is going to be the hypotenuse times cosine of theta. Therefore, mg cosine theta. And that force of gravity in the y is going to tell me what force is responsible for friction if there is friction. Okay? And again, that's why a lot of times you see it as force normal in the y, because when you look at force of friction, that's mu force normal. Well, in this case, it's going to be force normal in the y that is contributing to that force of friction. But again, some textbooks do it as force of gravity in the y. Okay? It's a preference of the publisher. So now we've got all this kind of settled out, let's take a look at a problem. It says a block of mass m is sitting on an inclined plane, which is 42 degrees to the horizontal. Assume a frictionless surface. So I'm going to draw my inclined plane. I'm going to draw my box. And now I'm going to start inserting forces. So the first one, again, is going to be my force of gravity. I'm going to have a force normal. I'm going to have that force of gravity or force normal in the y. I'm going to go and label as force normal in the y. And my force normal in the x. And because this is frictionless, if I were to draw a free body diagram of this scenario, I would have my point mass, I'd have my force of gravity, I would have my force normal, and then I would have my force normal on the x. If there was a force of friction, then I would have to draw that opposite of my force normal in the x, and it would need to be smaller than force normal in the x, because while this object is moving down that plane, force of friction is impeding part of that force. But this particular problem says there is no frictional force, so that would be my free body diagram that I've got off to the side. So now let's work what the problem actually asks. It says, what would be the expected acceleration down the ramp? Okay, so let's start out with a base equation that net force always equals mass times acceleration. And if I'm looking down this ramp, I'm looking in the x-axis. So I'm looking at net force in the x-axis would equal the mass times acceleration in the x-axis. Well, we've got another equation that says net force in that x-axis. Because there's no friction, this value of force normal in the x is my net force in the x-axis. And we just established in the previous screen that force normal in the x would end up equaling mg sine of theta. And luckily they tell us 42 degrees is my theta. So I can take this information and the relationship between these three equations. So, okay, well, if my first equation, net force in the x equals mass times acceleration in the x, but my net force in the x equals my force normal in the x, and force normal in the x is mg sine theta, therefore mass times acceleration in the x would have to equal mg sine theta. I can divide both sides by the common mass, and therefore acceleration would equal gravity times sine theta, which in this case is 42, all divided by nothing, because mass cancels out. Okay. So Now what I can do is plug in my acceleration due to gravity. So that is going to be 9.8 meters per second squared, all times sine of 42 degrees. And I get that acceleration in the x, or down that ramp, would be 6.56 meters per second squared. So if this were a frictionless surface, that would be its acceleration down the ramp. Part B, however, says the acceleration down the ramp is actually just 4.38 meters per second squared. That means there are frictional forces involved. Again, without frictional forces, 6.56 meters per second squared for the acceleration. 4.38 meters per second squared, less acceleration, means there's less force down that ramp than what we assumed there was. So now I need that mass of the block. So let's take a look at what all we've got. Mass is 3.5 kilograms. We know the actual acceleration along that x-axis is 4.38 meters per second squared. And we know that gravity is still 9.80 meters per second squared. Okay? And if you're wondering why I'm not putting a negative on that gravity, it's because for these type of situations where we would normally say we've got our things of positive, negative, etc. Well, because it's sliding down the ramp and I don't want to deal with negatives, in physics, the wonderful thing about it is that we don't have to stay with the normal convention. So we can set going towards the left as the positive. Likewise, I just as easily could have drawn this ramp as such and moved it towards the positive. Okay? If you're wondering, well, but it's moving downwards, that should be a negative. No, because all I've done is taken this axis and I've set it at a tilt. So my positive, my negative. That's still my x-axis. It just looks like it's running downhill. Okay? So one of those things about physics that will either irritate you to no end, or you'll come to just love the fact that it's odd in that manner. Okay? So I've got my information, and I can start backing and say, okay, so again, mass times acceleration is going to equal my net force. All I've done is taken equation 1 and rearranged it. And I know that now, previously I said it was my force normal in the x, which it still is, but now I have to subtract a force of friction. So we can set this up in much the same way, but we now include force of friction that is going to impede part of that force normal. And it's asking me, what is that force of friction? So that's my question. So we can now plug in values. I've got a mass of 3.5 kilograms. Acceleration, it tells me in the problem, is 4.38 meters per second squared. And that's going to equal my force normal in the x, which force normal in the x is going to end up being that mg sine theta. So 3.5 kilograms times gravity of 9.8 meters per second squared times the sine of theta, which was 42 degrees, not 40, sorry, 42 degrees, minus a force of friction. Okay. Now, if you wanted to, you could go into this, say mass times acceleration equals my force normal, which is mg sine theta minus force of friction, as an additional equation before you start substituting in numbers, which, word of caution to those of you who are watching this that are in AP Physics, that's what the AP Physics exam is going to want you to do first before you do any other rearrangement or substituting. Okay? But now I've got this equation, I can go on and solve for parts of it. So 3.5 times 4.38, I calculate to be 15.3 newtons would be the unit, equals 3.5 times 9.8, which is 22.9 newtons, minus force of friction. And in rearranging this, force of friction would therefore equal 22.9 newtons minus 15.3 newtons. So my force of friction comes out to be 7.65 newtons. And that's what the question was asking. So it turns out that while this force normal was 22.9 newtons, force of friction was acting backwards or in the opposite direction at 7.65 newtons, therefore giving you a net force of 15.3, which is what gives us the actual acceleration of 4.38 when you're thinking about that in reverse. So now it asks, what is the coefficient of friction? And for this, we go back to our equation that force of friction equals mu, or the coefficient of friction, times force normal. But that force normal, we go back up to our diagram, we're looking at force normal in the y, because force normal in the x is what moved us down the plane. Force normal in the y is what contributes to our frictional force. So this is where we're now going to go in and say, okay, my force of friction equals mu times force normal, but force normal equals mg cosine of theta. So mu times mg cosine theta. Therefore, 7.65 newtons equals mu times that mass of 3.5 kilograms times gravity of 9.80 meters per second squared times the cosine of 42 degrees. And when you rearrange and solve for that coefficient of friction, you should find 0.157. And there's no units on coefficients of friction because, as discussed in a previous video, that coefficient of friction is telling you what percent or decimal percent of an object's mass is resulting in frictional force, what decimal percent of an object's weight is contributing to frictional force, not mass, weight. So that is this problem, as well as kind of the overall concept of how you would set up the free body diagram for a mass on an inclined plane, how you'd be able to find the individual components of that force, and obviously how to then work those problems. So hopefully everything made sense. If not, feel free to leave me a comment, ask your questions. I'll make sure that I get back to you. Also, don't forget to subscribe to this channel so you don't miss out whenever I post new videos. And speaking of new videos, if you have any ideas for new videos, please post those in the comments as well, and I'll see what I can do. So thanks for joining me.